Okay, let's cover the next topic on optimization. This is on coordinate descent. Coordinate descent is an optimization technique, but it's a multivariate one, okay? So far, we've been seeing optimization, but they've been univariate, okay? Univariate optimization is pretty easy. Even if you don't have an algorithm, you can just brute force finding a minimum by doing what's called a grid search. A grid search is basically you just evaluate your function at a whole bunch of locations. And basically, when you plot a graph in R, you're effectively doing a grid search. It's not a grid search, but you're calculating the value of the function at a whole bunch of locations, and then R connects all of those values with a line. And so if in this following code, I have a very simple function, x squared minus 0.8x, and I create a sequence going from -3 to +3 with a step size of 0.001. So I've got about 6,000 locations here, and I just kind of plug these in, all right? And then I ask R which of these values is the minimum value of f. And when I do that, that's the 3,400 first location, and that corresponds to x being 0.4, and I can plug this in. And then when if you were to plot this, you can take f of x and kind of plot it, and that's what it does. But basically, this is a grid search, is you just evaluate the function at a whole bunch of locations, and then you say, hey, which of these values is the minimum? So that works fine, and that works pretty well for just a univariate function, okay? And you can extend the grid search to a multivariate function as well. However, the number of locations that you have to evaluate will grow exponentially. So let's say you have a function of two variables, x and y, and you want to evaluate a whole bunch of locations, let's say covering from one corner -3, -3 to +3, +3. And so if if they're spaced out at around 0.001, then you've got around 6,000 locations on each direction, and that evaluates to around 36 million locations to evaluate, right? You got 6,000 in the x direction, 6,000 in the y direction. I don't know why these dollar signs are showing up, but you got about 36 million locations to evaluate. If you have a third dimension, then you have 216 billion locations, and it just keeps growing exponentially like that. So multivariate optimization is a grid search just isn't going to work. Okay, so I'm going to introduce coordinate descent. And coordinate descent allows us to do optimization. And what it does is, if you have a multivariate function, you hold one of the variables constant, and then you hold all but one of the variables constant. Okay, so you select one of the variables and you say that's the variable I want to minimize. Everything else is held constant. So in a two-dimensional function, you hold x constant and then you minimize y. Then you hold y constant and you minimize x. If you have a three-dimensional function, x, y, z, okay, then you'll hold x and y constant and you minimize z. Then now that you get a value for z, then you hold x and z, y and z constant, and you minimize x. And then you'll hold x and z constant and minimize y, right? So you just kind of hold everything but one variable constant, and then you minimize the remaining variable, okay? So when you hold the other variables constant, that reduces the multivariate function to be a univariate function, and then you perform minimization on the univariate function. And then once you determine the minimum in that direction, you plug in that variable value, and then you perform univariate minimization for the next variable. So let me try to explain this with code. And so I believe this code is posted to to brew and learn. I'll make sure. All right. But let me just check here. I gotta sign on. Okay, so you have, coordinate descent.r. All right, so this uses a library called Plotly. You might need to install that. And I'm going to load up golden.r. What golden.r does is it's going to load in the golden section search function, okay? And so here's a two-dimensional function g, that I want to optimize, okay? And so I'm going to create our plots using Plotly. Now, don't use Plotly in your homework, okay? It takes too long to kind of plot and render, but it looks cool to do here. And so I'm going to actually plot this this function here in Plotly, and basically this function, x squared minus 2x minus 0.5xy plus 2.5y squared, is a paraboloid. It's basically kind of like a bowl, and we want to find the minimum of this bowl, okay? And so let me create a plot of this. Okay, and this is how it looks, okay? So one kind of cool thing about Plotly is you can like click and drag and do this, and so you can kind of follow, run the code yourself, and you can kind of see what it looks like, okay? And so when you look down from the top, you can see you have kind of this ellipse shape, and you have kind of these, I don't know, concentric ellipses. And but overall the shape is kind of like a bowl, but it's cut by the edges of this cube here, and we want to find the minimum, which is going to be somewhere around there. Okay, somewhere around there is going to be the minimum, but yeah, we're going to search for the minimum. We're going to do coordinate descent to do it. Okay. So I'm going to start at this arbitrary location where x is going to be -1 and y is going to be positive 1.5. So here, wait, let me turn this, orient this. How do I want to orient this? Okay. So here's x. X is -1 and y is positive 1.5. This is where we're going to start somewhere around here. Okay, around -1 and 1.5. We're going to start there, and so I'm going to add a marker right at that location. Keeps getting flipped around. So that's the location, -1, 1.5 right there, and I'm getting all kinds of warnings here. Okay, well, I'm not quite sure how to use Plotly 100%. It's producing plots, so I'm happy with that. But I think my code is not 100% accurate. And then also, by the way I'm running this, if you read this script, it's a terribly inefficient way to do it. But that's because as part of your homework, I want you to write this algorithm yourself. Okay, so first, I have this location. X is -1 and y is positive 1.5. And what I'm going to do is I'm going to hold one of these variables constant. So I'm going to hold y at 1.5 constant. All right, and that's going to reduce the function. So see this kind of line that's being traced out when I hold y at 1.5. It's going to reduce the function to a univariate function, and then we're going to minimize that univariate function using, a univariate optimization technique. Okay, so this is I'm going to write a function, and I'm going to basically take the function that I have, but I'm going to plug in y equals 1.5 here, and now this reduces to just be a function of x. And so I can plug in x, and I'm going to get back a value. So we'll do that, and I'm going to add a trace of that line to the plot here. So here it is, okay? So this blue line represents when y is held constant at 1.5, okay? And so from this angle, we can kind of see this is the function. This is just a line on the surface, but it's a univariate function, and we want to minimize this, okay? So where is the minimum of this parabola here in blue? That's going to look, it looks like it's, I don't know, somewhere around here, okay? Somewhere around here, that looks to be the minimum. So, you know, I can, there's a couple ways to minimize this, right? One is we could use calculus, and I could plug in y equals 1.5, and I get x squared minus 2x minus 0.5x times y, so that's what, minus 0.75x plus 2.5 y squared, so that goes away, so I get minus 2.75x, x squared minus 2.75x. I think the minimum there would be 2.7, what's 2.7 divided? 1.375. Here I can also use golden section search, okay? And so that's what I'm using here. I'm using the function golden to just say, hey, search for a minimum between x is negative 1.5 and x is positive 2. And when we do that, it says, yeah, the minimum here is when x is 1.375. And again, we could have figured this out ourselves. You know, again, writing out the function when if y is equal to 1.5, then, you know, I got x squared minus 2x minus 0.5 times x times 1.5, and that becomes x squared minus 2x minus 0.75x, and so that just becomes minus 2.75x. I mean, and then, you know, plus constants, right? Whatever this stuff, 2.5 y squared becomes, you know, constants, okay? And then, you know, if you take the derivative with respect to x, you get what? 2x minus 2.75 equals 0, and then so you get x is equal to 2.75, or 2x equals 2.75, and x is equal to 1.375. So we could have solved it doing calculus just as easily. But anyway, I did golden. We got x is 1.375. So let me plot that. That's going to be at x is 1.375. So we're going to put a dot like right around here. And that is the minimum of that blue line. The blue line's minimum is right here when x is 1.375 and y is held constant at 1.5. This is the value of the function. That's where it's minimized. Okay, so now that I have x is 1.375, we are going to find the one-dimensional function where x is 1.375, okay? And we'll plot that. So that will be a line going this way. So now it's a function of y, and x is held constant at 1.375 right here, okay? So we will we'll plot that, and I'll plot that line. And that's this line in, I don't know, purple, okay? That's this line. So this is where when we hold x constant at 1.375, and so we can see, yeah, this is a parabola right here. We want to find the minimum. It sure looks like the minimum is right around here, okay? Somewhere right around there. We want to find the minimum of this purple line, okay? So it's just a univariate function right on the surface here. Y is x is held at 1.375. So, you know, I would plug that in. This time x is equal to 1.375. And what was the original function? 2.5 y squared, okay? So basically, when x is here, this becomes a constant. constants minus, okay, 0.5 times 1.375 times y. So the original is what? X squared minus 2x. So that goes away to be constants, with respect to y. So I got minus 0.5 times 1.375 times y plus 2.5 y squared. Okay? And so what is 0.5 times 1.375? You get 0.6875. 0.6875. So I get negative 0.6875 plus 2.5 y squared. Okay? So then we take the derivative, and I get what? Negative 0.6875 plus 5y equals 0. All right, so I get 5y is equal to 0.6875. I'll divide by 5. And y is equal to, all right, so 0.6875 over 5. I get 0.1375. Okay, so y equals 0.1375. Now, I could have solved this using calculus like I did right here. Or I could just say, hey, computer, use golden section search, find the minimum. It says, the minimum's when y equals 0.1375. Okay. So no problem, we're going to go y right around 0.1375, somewhere right around there. That's going to be our minimum when y is right around there. So we will add a marker right there. Okay. All right, so this circle, this dot represents the minimum of the function right there. Yep, that looks like the minimum to me. And so now y is held constant. We're going to hold y constant at y equal to 0.1375, and we go through the process again, okay? And I don't feel like typing it all out here. So I'll just ask the computer. I just say, hey, plug in y equal to 0.1375 in here. Add a line there. And find the minimum. So the minimum happens when x is 0.1034375. And I say add the marker. Okay, and so here it goes. Okay, so we hold y constant at 0.1375. And then when you look at this function, we're already pretty close to the bottom here. But yeah, this green line is minimized right there, right? So you look at the green trace where y is held constant at 0.1375, and it's minimized when x is equal to 1.0343. 1.0343. So that's going to be right there. And you would continue this process of you hold one of these things constant. So the next step would be x is held constant at 1.034375, whatever that is. Okay, you hold x constant there, and the function, once you plug in a constant for x, boils down to just a function of y, and then you minimize that function, and you kind of keep going back and forth with this iterative, hold one constant, minimize the other variable, and then once you get that, you hold that variable constant, minimize the other variable. And you go back and forth, holding one thing constant and minimizing the other. Okay, and that's how coordinate descent works. Okay, coordinate descent, it's pretty effective. Like a lot of these other optimization techniques, it's not guaranteed to converge. You could have a really kind of wonky shape, and in that case, it's not gonna kind of work. So you can kind of imagine this. If you're on a hill or something, or on some kind of trek, and basically coordinate descent only allows you can either walk north-south or east-west. You can only basically turn, make 90-degree turns as far as the direction you're going. So, right, if you're trying to go downhill, it's going to feel a little bit awkward because you're going to be walking, you have to walk exactly north or south in one direction. And then once you feel like, okay, I've reached the bottom in this, if I keep going more north, I'm going to start climbing uphill again. So once you reach kind of the bottom there, you turn 90 degrees, either to your left or to your right, and you say, okay, now I'm going to head exactly east, okay? And you go east or whatever. And then you keep walking until you reach a point where you say, okay, now I feel like if I keep going east, I'm going to start walking uphill again. So then, you turn 90 degrees again and you start walking, I don't know, south or whatever it might be, okay? So, in this case, I guess we started here. We started walking east and we kept walking east until we reached right here where we reached the bottom. And then we say, okay, now we're going to, I guess, walk south. And we get here. And then once we got here, we say, okay, now I'm going to walk west. And then I take just a few steps, right? If you weren't restricted to going left or right only, you could kind of just start walking diagonally down the hill. And that would be probably more efficient. That is known as gradient descent. That's a different optimization technique, not covered in our class. Coordinate descent just goes one direction at a time and performs univariate optimization. And again, how you do your univariate optimization is up to you. Here I used golden section search in this code. I also showed you, you could have just used plain old calculus to optimize the function. So, or, any of the other optimization, Newton-Raphson, whatever you want to use, you can do it. Okay, that is it for coordinate descent. The script is posted to Brew and Learn, so you can kind of check it out. And good luck as you code this up in your homework.